study about the type of input test signals used to find out the time response of a system. Then we will study that what is called the type of a system and what is called the order of the system. So let's start. First, we will study about the type of input test signals. As we know that the input signals, the various types of input signals, they are used to find out the time response of a system. That is, we will apply various input signals to a system and then we will analyze the output of the system for these various inputs. Okay, so what is the use of these input signals? So these input test signals, they are so choose that the system response, it reveals significant properties of the system and also it gives us the information about the physical behavior of the system. Now let us study that what are the standard input test signals which are used to analyze the performance of the system. The first input test signal is step input. So a step input is a sudden change of the reference input at t equals to 0. That is, when the time is 0, the input suddenly changes to a value. If we draw the graph for the step input, it will be like on the x-axis we will draw the time, that is t, and on the y-axis we will draw the amplitude. So this amplitude is suppose represented by rt, that is the input signal, and this step input is having the amplitude here a. Okay, this is t equals to 0. So step input is that it is a sudden change of the reference input at t equals to 0. It means that at t equals to 0, it is suddenly changing from 0 to a value. Here it is a. So a is the amplitude of this step input. Now if we mathematically represent this step input, it will be like rt will be equals to a, that is the amplitude, multiply with the step input. Okay, because step input is having the value as 1, so if we are multiplying it with a constant a, so it will be shifted to the position of a having that amplitude. Now here ut, it is the step input, so we will define ut as it is 0 for t less than 0 and it is 1 for t greater than or equals to 0. So if we draw the signal for it, it will be like this is the time, this is ut, and for time less than 0 it is 0, that it will be 0 here, and this is t equals to 0. So at t equals to 0 and greater than, it is having the value 1. So it is suddenly changing the value at t equals to 0 from 0 to 1. Okay, and when this step input it is multiplied with the amplitude A, then it will shift to the position A. Okay, so RT is A UT, where A is a constant. Now this is the Laplace transform of, it will be Laplace transform of A by S. So AUT, its Laplace transform is A by S. Okay. Now if we take the value of A as 1, then this step unit or the function UT is called step function. Okay, or we can say unit step function when the value of A is 1. So in this way we will define the first input test signal, that is step input. Now take the second function, second input signal, it is ramp input. So ramp input is having a constant velocity. As we have seen that the step input it was having a constant amplitude. So the ramp input it is having a constant velocity, and we can mathematically represent it in the form RT equals to 0 for t less than 0, and it is 8t at t greater than equals to 0. So this is how we mathematically define it. If we draw the graph for it, it will be like, here we have the time t, it is the signal RT, and it is a straight line. So this straight line is having the slope as constant, that is A. Okay, and this signal is A T, that is the amplitude, the slope multiplied with the time. So this is how we mathematically define the ramp input. Now A is the slope and its Laplace transform of the ramp input is A by S square. Okay. Now if this A, that is the constant, it is equals to 1, then it is known as unit ramp function. Okay, that is if the amplitude is 1, then it will become unit ramp function, otherwise it is a ramp input. Okay, now the third input, it is, we have parabolic input. This is also known as step acceleration. Okay, so how we define it? So the ramp input, it was having constant velocity. So the parabolic input, it is having constant acceleration. Okay, and how we can mathematically represent it? We have the signal RT. It will be given as 0, again for t less than 0, and for t greater than equals to 0, it is given by a t square by 2. Okay, so this is the mathematical representation of the parabolic input. Now if we draw the graph, it will be like this. Is again time t, this is the signal rt, and this time we are having a parabola. Okay, and this is the signal a t square by 2. So this is a parabolic input. Okay, now here we have this a, so a is a real function this time, and Laplace transform will be of this function will be a by s cube. Okay, so this is the parabolic input. We have studied 3 inputs here. Now the fourth input is impulse input. So the impulse input is having 0 value everywhere. That is from whatever, if we draw it on this line where we have the time t. So everywhere on this time axis it is having 0 value except at t equals to 0. So if we have t equals to 0 here, so at t equals to 0, its magnitude is infinite. That is, if this is the signal RT, then its magnitude will be infinite at t equals to 0. And on the other, that is on the positive and the negative time, it is having all the, at all these instants, it is having the magnitude 0. Okay, except at t equals to 0, here it will have the magnitude as infinite. Okay, so this is an impulse input. Now if we mathematically represent it, it will be del t equals to, this is the representation of the impulse input. It is 0 for t not equals to 0, and when t is equals to 0, it is infinite. Okay, now we know that the impulse input, it is not having the amplitude. Amplitude is infinite, but its duration, okay, that is the duration of the impulse, what it is 0. Okay, so this type of function, it is called impulse function. Okay, it becomes an impulse function. That is a function which is having amplitude as infinite but duration as 0. Now this impulse function, it is sometimes also called delta function. That is why we have represented it as del t. Okay, this is called del because it is also known as delta function. Okay, so these were the 4 inputs which we apply to a system to analyze its response. Okay, the first input was step input, then ramp, then parabolic, and the last is the impulse input. Now keep one thing in mind, there is a special note for in it, that the step function or the step input is a first time derivative of ramp function. Okay, step input is a first time derivative of ramp function, and impulse function is defined as a first time derivative of step function. So these three functions, they are linked to each other. Step function is the derivative of ramp function, and impulse function is defined as a derivative of step function. So if we write it in this way, we have unit impulse function equals to d by dt, that is first time derivative of unit step function, and unit step So if we take Laplace transform of unit impulse function, it will be equals to Laplace transform of del t, it will be equals to 1. Okay, so this is the special note on this input test signals which you have to keep in mind, that step function is a first time derivative of ramp function, and impulse function is the first time derivative of step function. Okay, so this was all about the types of input test signals. Now we will study the next topic of this video, that is what is the type of a system. Whenever we see a control system, whenever we see the transfer function of a system, then how we can determine that what is the type of a system. Okay, so let's define it. If we want to represent the open loop transfer function, we have seen that GS upon 1 plus GSHS is the closed loop transfer function of a control system. Okay, and in this transfer function GSHS, this which we are having, GS is the forward path gain and GSHS is the open loop transfer function. Okay, so if we represent the open loop transfer function of a system, it is given by GSHS equals to Okay, so GSHS is defined as this. We have factorized the numerator and the denominator polynomial, so it can be represented in this way, that is the factorized form. So here K is the forward path gain and Sn, it represents pole of multiplicity n. Pole of multiplicity n because the factors of the denominator polynomial, they are known as the poles, and the factors of the numerator polynomial, they are known as the zeros of the system. So this is the pole, one of the pole of the system which is having the multiplicity n. That is, there are n factors, n poles. Okay, so this is the multiplicity n at the origin of the complex plane. Okay, this you will understand. Let's take an example so that you can clearly understand it. We have GSHS as, we suppose, 10 s plus 1 upon s3 s plus 2 s plus 4. This is an open loop transfer function. Now here we are having, if we see the factors or if we see the poles of this system, then it will be s3, s to the power 3 equals to 0, s plus 2 equals to 0, and s plus 4 equals to 0. So we will have, so if we take out the poles of the system, it will be s equals to 0, s equals to 0, and s equals to 0 three times, because here we are having s cube. Then we have s equals to minus 2 and s equals to minus 4. So what it is saying, that s to the power n, it represents the pole of multiplicity n, that is here pole of multiplicity 3, because there are 3 multiples at the origin, because it is the origin of the complex plane. Okay, so it is the definition of s to the power n, that what it represents. Now here n is the number of poles at the origin. Okay, so what will be the type? This n, whatever be the power of the s n, it will be called as the type of the system. Okay, that is in the example which we have taken, as we are having the power of s, that is n, as 3, so it will be a type 3 system. Okay, so n, if n is equals to 0 for type 0 system, n will be equals to 1 for type 1 system. Similarly, for n equals to 2, n equals to 3, we will have for type 2, type 3. Okay, so this n, that is the pole of multiplicity at the origin, it defines the type of the system. Okay, now next let us see that what is the order of the system. Earlier we have defined the open loop transfer function. Now let us see the closed loop transfer function. What it will be like? This is TS, the closed loop transfer function. We can represent it in the form of the equations. Okay, so this is the closed loop transfer function. Now here, the order of the system is defined as highest power of s in the denominator polynomial. Okay, so in this is the numerator polynomial, it is the denominator polynomial. So you have to consider this denominator polynomial and the highest power of s. In this we are having highest power as n. So this highest power will define the order of the system. Okay, so n is the order of the system. Let's take an example. We have the transfer function gs upon 1 plus gs hs, that is the transfer function, as k s plus 2, and we have s squared plus 1, and here we are having s squared plus 1. Okay, so if we multiply it, we will get the highest power as s to the power 4. So 4 is the order of the system. That is, it is a fourth order system. Okay, for n equals to 1, it is first order system. N equals to 2, second order system. Similarly, we will define the systems. Okay, so type was the pole of multiplicity, that is the common. If we take out common here, and then the power of s will be the type of the system, and n order will be the highest power of s in the denominator polynomial. So in this video, we have studied about the types of input test signals which we use for analyzing the performance of the system. Then we studied that what is called the type of the system and order of the system. I hope this video is clear to you. Thank you.